and then we'll crack on. Okay, so welcome to anybody who's just joined us. As I said before, it's Intro to Statistics, or at least I hope it is. It's week 6, and we're going to do some of the exercise sheet. As always, we have Hayden here, who is able to ask questions and will be on the chat. So if you've got any questions about any of the course content this week and previous weeks, Hayden should be able to help you in the chat. I will try and keep an eye on it as well. So if you want to put in there anything like, I can't see the visualizer, need to move the paper up, what the hell are you talking about? That's all very, 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 very welcome. Don't forget that you can direct message people, both me and Hayden and each other. So if there's anybody in the class that you know that you want to talk about the content to, please feel free to do that while the session is ongoing. It's just going to be run exactly the same as the previous 2 classes that I've taken with you. So what we're going to be doing is we're going to be doing some of question 3, 4, 5, and 10. We're going to see how far we get. As we go along, I'm going to give you some little breaks so that you can try and do the next step or try and double check your working. It doesn't really matter whether you've tried these questions in advance or not, but if you haven't tried them in advance, just be aware that maybe some of the calculation gaps are going to be a little tiny bit short, just to try and accommodate the fact that you should have at least tried before arriving. So, you know, don't feel like, you know, you're off target if you can't, you know, calculate what I'm asking to in the 1 or 2 minutes provided. Okay, so I'm going to switch over to the visualizer. We'll go from there. So the first question we're going to look at is number 3. And question 3 is quite straightforward, but it's going to help us with question 4 and question 5. So it's going to have some of those key ideas in that we're going to need. So what it said was that we've got n random, just going to let somebody else in. We've got n random variables from a random sample, and each of them is normally distributed, and we're asked some properties of the sample distribution mean. So let's have a look at what we've got. So we've got x1 through x25, and each of these are their IID, so independently identically distributed, and each of the i's is, that is not nice, Lucas. I'll try and make it a bit harder there for you. Okay, I'll just try and write a little bit bigger as well. So each of the xi is normally distributed with mean 112 and variance 12 squared. Okay. So the first part of the question is bookwork, and we were asked, what's the sampling distribution? So what's the distribution of x bar 25? Okay, now hopefully we've seen this an awful lot by now, and we should be clear that x25 is going to be normally distributed because it's the sample distribution mean, and its mean is going to be the mean of the underlying data, so mu, and its variance is going to be related to the variance of the its mean is going to be the same as the mean of the data, and its variance is going to be related to the variance of the underlying distribution, which is sigma squared divided by n, where sigma squared there is the variance of the underlying distribution. So we're going to have 12 squared divided by 25 because we've got 25 points in our sample set. So that's the distribution of x bar 25 that we're interested in. Now the next part of the question was asking us for a probability, and we were asked for the probability that x bar 25 is bigger than 115. So it is helpful if we're able to answer part A in order to be able to do this, because we can use it for part B. So we've got x bar 25, which we know the distribution of. So we should be fine with calculating this probability here. Now, the first thing I want to do is I want to write this the other way around, because I just want to be able to write it in terms of a CDF, which I'm going to be able to calculate because I know the distribution of x bar 25. So I'm going to go for 1 minus and then the probability and change the direction of this inequality. Okay, and then this one here, hopefully I can see that that's a normally distributed random variable, so I could standardize my x bar 25 and then go from there. Okay. So when I'm standardizing, I'm taking off the mean and I'm dividing by the variance so that I end up with a random variable that's normally distributed with parameters 0 and 1. Okay. And I need to do the same to whatever's on the other side of the
Answer. Right.
That's not right. So have I divided by the wrong thing? Yeah. Of course I have. I need to take the square root, don't I? So when I standardized, I made an error there. I should have been taking the square root because I should have been dividing by the standard deviation. So thanks for picking that up. Okay, so I've got myself in this situation. And in this here, I'm going to define it as Z, and I know that this is an all-rounded variable with parentheses 0 and 1. And I can look this up in the table, can't I? So I know that this is 1 minus this one. Yep. And hopefully I'm good enough with my table to be able to find that it's 0.1057. Okay. So part C was really, really similar. The tricky bit, the only tricky bit, was deciding what probability that I needed to be actually looking at. So I was given a statement, like a wordy statement. Okay, send it outside still. And what I was asked was X bar 25 deviates from mu by no more than 1. Okay, so I need to find some mathematical way of doing this. And I think that where we want to start with is that the absolute value of the difference between 25 and mu is less than 1. And you're fine to jump in there. This is also equivalent to that minus 1 is less than X bar 25 minus mu is less than 1. Or mu minus 1 is less than X bar 25 less than mu plus 1. So feel free to start with any one of those three, but you're going to find it easier to start with possibly the middle one, because you're a little bit of the way there towards standardizing X25 already. So hopefully you can express the probability of the middle one in terms of the CDF of the normal distribution. So that's the first thing I'd like you to maybe write down is how can I express the probability of this one in terms of the CDF of the normal distribution. So hopefully that like immediately pops out at you, as we need to do the same thing as before. We need to standardize so that we can use the table that we know. So we need to do the same thing, don't we? We need to divide by the square root of 12 squared over 25. And the other difficulty we've got is we've got two inequalities in there. We've got this one and this one. So when we've got an interval rather than, well, we always have an interval, but when we've got an interval that's, not going to infinity on one side, we have to take a difference between the CDFs. So hopefully, what you were thinking of is we can write.
哦，那个你今天去郑州了是吗？你说。那个啥呀，我
Got somebody who's not on mute. Never mind. Okay. Right. So yeah. So let's standardize first. Standardize first. So this one. Minus 1. X bar 25 minus 1 divided by square root 12 squared minus 25. I just said divided by 25. And then these have to be divided by the same factor. So again, because we've got the two inequalities there, we're going to have a difference. And we need to put first this one and then this one. Okay. And hopefully you're happy with basically the fact that the square root of a ratio is the ratio of the square roots. And each of these, so we also know what square root of 25 is, it's 5, right? We can look these two up in the table. And what we should be looking up is the value of 0.417 and minus 0.417. So when we've got an interval like this and we're saying like a deviation, so the absolute value is less than a certain value, I'm always going to end up with a number here and the negative of whatever is in the first one in the second one. So it's a little bit like a sense check for yourself. It's like, oh, have I screwed something up with the standardizing? Hopefully not if you've got some symmetry in this expression. Yeah? And then if I look those up, I should be getting 0.3234. Okay, so I've given you an awful lot of information for this one. I've pretty much done this one for you. Now, the next one is very, very similar. But we just need to get ourselves started. So in order to get yourself started, on question 4, what I would like you to try and do is write down what the distribution of x bar 10 and y bar 15 are if the xi are normally distributed with parameters 20 and 3 for I between 1 and 10, and the yi are normally distributed with parameters 20 and 3 for I between 1 and 15. And then have a think about what's the distribution of x bar 10 minus y bar 15. So that's sort of like my little hint to get you started. So I'll give you a couple of minutes to have a little think about that, and we'll come back and get that down on paper, because once we have that, hopefully that'll be enough of a hint to combine it with question 3 to get us to the answer. Okay, so with x bar 10, it's a sample distribution mean. So I know that it's going to be normally distributed. And I know that the mean of this guy, so the mean of the sample mean is going to be the same as the population mean. So I'm just able to lift the 20 from here. And the variance, I need to scale by, the number of elements in the sample. So I need to go for 3 divided by 10. And the same with y bar 15. I've got the mean of this sample as 20 still, and the variance is going to be 3 divided by 15. That's because there's 15 elements in y. Yeah. So I think one of the things that I really struggled with when I first saw this type of material is I was thinking, well, so X bar is just a property of a sample, right? So I've taken one sample and I'm thinking, yes, so I've taken lots of random variables that are normally distributed, and then I take the mean of them. Why does this thing have a distribution? I just took a sample, and then I'm calculating the mean. Like why and how? And one of my other thoughts there was often like, but I took them from a distribution that was not normally distributed. How has this managed to happen? That they've got this kind of distribution. And I think why that was really bothering me is because I wasn't realizing, or I wasn't always completely conscious of the fact that in principle, I was being asked to take a lot of different samples, so or you know, that I didn't actually know what the values in that sample were yet. So it was more of a hypothetical question, in the sense that it was maybe if I took 10 items, 10 random variables from this sample, what kind of features would they have? The idea was coming back to, well, you're going to do this lots and lots of times, and you want to be able to say from those lots and lots of times something about the underlying data. So, you know, really have a solid think about, you know, why is this a random variable? Because I think getting over that hurdle is, you know, basically key to, you know, really motivating why on earth we do these types of things. So with those two in mind, hopefully we would be able to know what the difference is, because we know how to calculate the distribution of the difference between two random variables. So the difference between x bar 10 and y bar 15 is the difference between two normally distributed random variables. So it's still going to be normal. And the mean, well, both of them have mean 20, so hopefully the difference has mean 0. And then the variance, well, the variances I have to add up, despite the fact that I'm taking the difference here. So I'd end up with 3 over 10 plus 3 over 15. And if you can work this out, it's exactly a half. So normal parameters 0.5. And then we're nearly there, because what we're being asked for is we're being asked for the probability that the absolute value of this difference between x bar 10 and y bar 15 is bigger than 30%, so bigger than 0.3. And you should be able to use an approach really similar to that we did in question 3 to proceed. So you see we've ended up with an expression that's nearly exactly like this. Well, it's not actually. The inequality is the other way around. So that should give us an idea of the first thing that we need to do. And then when we had an event like this, we were able to write it as the difference between the CDFs. So I want to just give you just a moment just to finish that off from that point. So hopefully you can just replicate the approach from question 3 to get your final answer. And when you've given it a try, I'll give you what the answer is and we'll carry on. Okay, so I hope. No, in fact, I know that you'll have been able to give this a solid crack. That we end up with the difference between the CDF at normal distribution 0.3 divided by the square root of half minus and then the negative is minus 0.3 divided by the square root of half. And the answer overall is so 1 minus. You see, that's a very common mistake going on there. So overall in the question, we were asked that this is bigger than. But as I mentioned before, when we find the difference, we're going for less than. So I should have a 1 minus at the beginning here. So I should have 1 minus and then distant and then plus the negative one. And overall, I should end up with 0.67. Hopefully. Hopefully you can see that. All right. So I'm going a bit slower than I'd hoped, as always. So let's just try and get the idea down for question 5, and then we can crack on with question 10. So question 5 was one of these confusing, well, one of these ones that historically, when I very first saw this material over a decade ago, would have been one of the ones that would have confused me. And the reason being is that I've started off with two sequences of random variables which are not normal, and I end up with something which is effectively a normal distribution. So and I find that students overall don't like these types of questions. When we teach probability 1, these are also the types of questions that students don't really like that much, is ones where you start off with one distribution and then you have to use a different distribution for some reason. It tends to be like, well, why have we changed? Or really being difficult to decide unless you've got a deep understanding of the material, why you're switching from one approach to another, or what the connections between various distributions are. So that's why we'll motivate this one with the approach that we're going to take. So I'm going to define two random variables. I'm going to define x to be a binomial distribution. And I'm going to say there's 200 elements in that binomial distribution, and 65% chance of success. So what X is going to be telling me is it's going to be telling me the number of people who support candidate A in the first sample. Okay. Now, the reason why I can say it's binomial is because I can say, well, even though there might be 20 people to vote for, whether or not they're supporting candidate A is going to be a yes or a no. I'm able to bundle the support for all of the other candidates together. And then hopefully everybody's vote is independent, or at least I can reasonably assume that. We're thinking probably the parameter is 65%. We're expecting 65% of people to support candidate A. And I can define Y similarly, also binomial 200 and 0.65. I'm going to assume that X and Y are independent. So how many people are voting for candidate A in the two areas is going to be independent. And that might not necessarily be true in real life. So to get us started in the direction of calculating the probabilities, I want to maybe think about what is the distribution of, or how can I approximate these binomial distributions with a normal distribution? So so hopefully you can remember that, so if Z is binomially distributed with parameters N and P, we can say that X is approximately approximately distributed normal, and then the parameters are N times P and NP 1 minus P. So this one, N times P is going to be the mean of the distribution of X, and then NP 1 minus P is the variance of X, of the mean of variance of X. Okay. Oh, having a moment. All right. So if that is, so if we recall that that's how we approximate the distribution of a binomial random variable with a normal distribution, how can I write down the distribution? So how can I approximate X divided by 200 and Y divided by 200 using the normal distribution? Okay. So I could just put in the parameters that I was given here, so 20 and 0.25 into this representation, but this wouldn't give me X divided by 200. It would give me the distribution, an approximate distribution just for X. So what happens when I divide I multiply a random variable by a constant? How does that affect the mean, and how does it affect the variance? So have a little think. It should immediately pop out at you. How can I write an approximate distribution for X divided by 200? What do I need to change about this formula? I'm going to put these two numbers in. Okay, so somebody John has actually told everybody what to do in the chat, which is amazing. He's saying, well, when we've got a constant times by a random variable there, we need to divide the mean by times the mean by the constant. So in this case, divide the mean by 200, and we need to divide the variance by 200 squared. So what we're going to end up with is we're going to end up with just P here, so 0.65. And then this one is going to be 0.65 for P times 0.35, which is the 1 minus P. And then we're going to have divided by 200 squared. But we've got one set of 200 here, so we're going to have divided by 200 here. So thank you, John. It's amazing. So now hopefully we're ready to go. Because what we've been asked for is the probability that the difference between X minus Y divided by 200 is less than 0.1. So the percent, so X divided by 200 and Y divided by 200 are the percentage of people supporting candidate A in area 1 and 2. And the absolute difference between these needs to be less than 10%. So this was the probability that we were asked for. And given that we know this one, and we know that Y has exactly the same distribution and is independent, we should be able to proceed to calculate this one using the same approach as we did in question 3 and 4. So I'm going to leave that to you. hopefully with that hint, you can now get through that perfectly. We're going to continue having a think about the binomial distribution in question 10. And I realise that we've only got 5 minutes left, but I think we should at least be able to do the bias section of question 10. So we were given n random variables, x1, x2, up to xn. We were told that these are IID and that xi is distributed binomial m and p, and we don't know p. Okay. Now, again, be careful that n is the number of x's that we've got, and m is to do with the distribution of each of the individual x's. So just be a tiny bit careful there. And we were given a possible estimator, our candidate estimator. We were asked maybe we could estimate p using p hat, and this was going to be the sample mean plus 1 divided by n plus 2. So that was our proposed estimator. And what we were asked to do is to find out whether or not this one was biased. So calculate the bias of p hat. Okay, so hopefully we can proceed with just one little tip. So what was the bias? It was the difference between what I expect the value of this estimated to be and what the actual parameter is. So it's going to be the expectation of p hat minus p. Okay, so hopefully you can manage that, because hopefully you can remember from what we were just saying, you know, some properties of the binomial distribution and what the mean and variance are. So I'll just give you a second just to check over your answer for that. Or to work it out. Okay, so there, all I've used is that the expected value of the sample mean is going to be exactly the same as the mean of each of the individual random variables, and the mean of the xi, because it's binomially distributed with parameters m and p, is going to be mp. So I should have that. I've missed off my minus p from here, so I'm going to add that back on. Okay. And if I rearrange this, so to gather up my p's, I'm going to end up with 1 over 1 plus n plus 2 minus p, and then n plus 2 minus n plus 2 divided by n plus 2. And then the second part of the question was about what happens to this asymptotically. So what happens to this when n gets really, really big? So, oh dear. So hopefully you can see why I've rearranged it into this form now, because we can immediately see what's going to happen to both of these terms. So with this first fraction, as n gets really, really big, what's on the bottom of this fraction is going to explode up to infinity. So this is going to go to 0. And then what about this one here? So here I'm going to have n plus 2 minus m and n plus 2. And I think that one's probably going to go to 1 because the bigger n is, the less difference there's going to be between the top and the bottom of this fraction. Okay. So as n tends to infinity, we've got the bias is asymptotically going to be equal to minus p, because I'm going to have 0 here and 1 here. So that's an asymptotically biased estimator, isn't it? Because in the limit, as n tends to infinity, this bias is, not going to 0. So that's not the type of estimator that we would ideally like. Now, I've completely run out of time, and I need to let you all go so that Sarah Elise can have his next class all come in. So I hope that that was helpful, and I hope that you've managed to have a good crack at these exercises. If you've got any questions at all about anything, you please feel free to email me, email Sarah Elise, ask in the chat next time you're here, or anything of that type. So feel free to leave if you would like, or hang around and listen to Sarah Elise do it all over again. Okay, I'm going to go, Sarah Elise.
Okay, thank you, Jenny.
Yeah, all right. See you
Take care. Have a good day.
Bye-bye.
Hello guys, good morning or good afternoon. Hope you are well. Uh, Hello guys, are you okay? All right guys, welcome to tutorial sheet 6. All right, let me show you the tutorial sheet. I hope you have already looked at it. If you haven't looked at your tutorial sheet, this is it, right? So this is the tutorial number 6. As you can see, there are 10 questions. I will try to do as many as possible. Maybe, I don't know, depending on the time I have, I will try to do as many as I can. Okay. All right, guys. Now let's begin. As usual, if you have questions, please use the chat room, right? Right. And any questions you guys have, please use the chat room. Okay. So this is the. I hope you can see this. I hope you can see this visualizer. Let me try to refocus it. I don't know if you can see it better now. Okay. All right, guys. So as you said, let me start with question 10 first and work backwards, because question 10 is the most recent stuff I did. All right, so I will start with question 10. Question 10 says that you have this estimator, and the question is to find the bias and the variance of this estimator when the random sample is from a binomial with parameters m and p. All right. Okay, guys. So let's begin. So this is question number 10. Hopefully you can see this. So you have a random sample x1 to xn, IID, from a binomial distribution with parameters m and p. Right? And what you are given is an estimator for p, which is this, right? Okay, it's x bar plus 1 divided by n plus 2. Now the question is to find the bias and the variance of this estimator. Right, now remember the definition of bias. The bias of an estimator is defined as the expectation of that estimator minus the parameter that you're trying to estimate, right? Okay, so in this case, it's the expectation of x bar plus 1. Okay, so this is the expectation of and this is you should take the expectation inside, you get right? Now remember, x bar is the sample mean. So you can write it as the expectation of 1 over n times the sum of xi. Yeah, you guys okay with me so far? Any questions, please feel use the chat room, guys. Right, now you should take the expectation inside the open bracket. This is what you will get. Yeah. Now, I'm sure you know that if you have a variable that is binomial with parameters m and p, the expected value is, you should know this from probability 1. Hello, guys. The expectation of a binomial variable with parameters m and p is m times p. Do you remember? I'm sure all of you know this, right? Don't you? Okay. Now m times p is a constant with respect to I, and the sum of a constant is n times the constant. So this is n times the constant, which is mp. Okay. Now you can put this together as mp plus 1 divided by n plus 2 minus p. Okay, so this is the bias. This is the bias of the estimator for p hat, the bias of p hat, right? Now this guy here, you should take the limit as n goes to infinity. This goes to, the first one goes to 0. So you have 0 minus p, which is minus p. Yes, n goes to infinity, right? Okay, so you may recall from last week that an estimator is said to be asymptotically unbiased if the limit of the bias is 0 as n goes to infinity. But in this case, the limit is not 0. So what this implies is that p hat is not asymptotically unbiased for p. All right, are you okay with this, guys, or no? Remember the definition of asymptotically unbiased, guys. It means that the definition says that the limit of the bias must be 0, but in this case it is not 0. So the estimator is not asymptotically unbiased. Are you okay with this, guys? So this is part 1 of question 10. Any questions, guys? Anything which is not clear, please let me know. Are all of you okay? Talk to me, guys, please. Yeah, sure. All right. So that's part 1 of question 10. Part 2 of question 10 is to find the variance of p hat, right? Which is the variance of x bar plus 1 divided by n plus 2. Oh, sorry. Okay, so this is the variance of x bar divided by n plus 2 plus 1 over n plus 2. Okay. Now remember, this is a random variable, this is a constant. You should know that the variance of a random variable plus a constant is the same as the variance of the random variable. In other words, the constant does not affect the variance. Do you remember this? Do you remember this fact from probability 1? Hello guys, talk to me. All right, and also when you have a constant, when you pull out the constant outside, you need to square. You need to square that, right? So it becomes variance of x bar. So this is 1 over n plus 2 squared times the variance of this, yeah. Now, if you pull the n outside of the bracket, you need to square it one more time. All right, so it becomes times 1 over n squared. And taking the variance inside the summation, you get this. Are you with me okay so far? Hello guys, talk to me please. Any questions, feel free to talk to me guys. Now, what's the variance of a binomial? I'm sure you know. The variance of a binomial is mp times 1 minus p. Yeah. Now this guy is a constant. With respect to I, mp times 1 minus p is a constant. So what you can write is the following. Is n times the constant, which is this, right? Now the n cancels with this, so the final answer that you're going to get is the following. Is this, right? All right, so this is the answer for the part 2 of question 10. And as n goes to infinity, this goes to 0 as n goes to infinity. All right, guys, so this completes the solutions to question number 10. Are you okay with this? So before I go to question 9. So if you just joined me, I'm just working backwards from question 10 to question 1. So I just finished the solutions to question 10. Are you okay with this, guys? All of you okay with that? You sure? All right, so let me go to the next question. So we're done with this one. The next question is question 9. So here you have a random sample from a uniform 0 theta, and you have this estimator theta hat equal to k times x bar. And the first part is to find the k so that this estimator is unbiased for theta. Okay, so let me show you how to do this. So this is question number 9. You have a random sample x1 to xn from a uniform distribution. So this is IID, a uniform, uniform 0 theta, right? And you have an estimator for theta, which is k times x bar. The question is, we want to find the k so that this estimator is unbiased for theta. So what you need to do, guys, is you need to find the bias you need to find the bias of theta hat and set it equal to 0. Okay. And then solve for k, right? Now you may recall that the bias is defined as this, right? As usual, right? And this is the expectation of k times x bar minus theta. And this is k times the expectation of x bar minus theta, right? And this is k times the expectation x bar is 1 over n times the sum of xi minus theta. All right, now you should take the expectation inside the summation. You get this. Yeah. Right. Now, do you guys remember remember xi has this distribution, uniform 0 theta. Do you guys remember the expected value of if you don't remember, let me show you. If you have a variable x that is uniformly distributed on the interval from a to b, then the expected value of x is a plus b divided by 2. You remember this result, guys, or no? This is something you should have learned in probability 1. If you don't know this, I'm sure most of you know this, maybe all of you know this result, right? Or don't you? Okay. So using this result, the expectation of xi is equal to it's equal to this, right? Now theta by 2 is a constant with respect to I. So what you have is k over n multiplied by n theta by 2 minus theta, right? Now the two n's cancel out. So you get k theta by 2 minus theta. And this is equal to 0 if and only if k is equal to 2. All right. So the conclusion is that theta hat equal to 2 times x bar, right, is an all right, guys. Are you okay with this before I do the second part? Hello, guys. Talk to me, please. Any questions on the first part of question 9, which I just did? Use the chat box. Are you okay? All right. Thank you. All right. So the conclusion of the first part is that this estimator is unbiased for theta, right? So I'm going to now do the second part of question 9. Here we are. All right, so this is part 2 of question 9. So the part 2 is asking you to find the variance, the variance of 2 times x bar, right? Now 2, if you pull it outside, it becomes 4 times the variance of x bar, okay? So this is 4 times the variance of 1 over n times the sum of xi. Okay. Now, if you pull the n outside of the brackets, it becomes 4 divided by n squared times the sum 1 to n of the variance of xi. Okay. Now I'm sure you guys know that if you have a variable x that has the uniform distribution on the interval a to b, then the variance of x is equal to this, right? Do you remember this, guys, or not? I'm sure you know that, right? Yeah. So let me put this in a box. This is a well-known result, right? Okay. Now using this result, you can write the above as 4 divided by n squared times the sum 1 to n of theta squared divided by 12. Okay. Now theta squared divided by 12 is a constant with respect to I. Okay, so what you have is 4 divided by n squared multiplied by n times the constant, which is theta squared by 12. All right. So the final conclusion is that this you have theta squared divided by 3n. So that's the variance of x of the estimator. And as n goes to infinity, this goes to 0, which is a good thing. So this estimator has bias equal to 0 and the variance approaching 0 too. All right, so it has all the good properties of a good estimator, right? All right, guys, are you? So this completes the solution to question 9. Now, before I do question 8, are you okay with this? Hello, guys, talk to me, all of you. Okay, thank you, guys. I'm disappointed with the number of people turning up for the tutorials. I mean, I don't know why there are so few turning up. And by the way, just a reminder that the quiz 5 is due on Thursday this week. So if you haven't done so, please submit your quiz 5 before or by 10 o'clock UK time. Okay, on Thursday of this week. I have done 20 questions. I mean, I worked out 20 questions on quiz 5, so you should have no excuses for not doing well. All right. Anyway, let's look at question 8. Question 8, you have a random sample from a population with mean equal to 0, variance sigma squared. The first part is to find k. K is a constant such that this is an unbiased estimator of sigma squared. Right. Right. So this is question 8. Yeah. So what you have is the following estimator. And we want to find the k such that this estimator is unbiased for sigma squared. So what you need to do is to find the bias of this, right? Which is this, yeah. All right, and then set this to 0 and then solve for k. Right. Let me show you how to do it. Right, so this is this. Now I'm going to pull out the k outside and I'm going to bring the expectation inside. So this is what you will get. You will get k Okay, this is what you get. All right, in the next step, I'm gonna introduce a trick. It's not a trick, it's kind of a rearrangement. You will see why I'm doing this in a sec. Right? You see what I've done here. I have introduced this term minus of this term, and also introduced plus of the same term. So I haven't changed anything. The reason I have done this is because of this. Can you recognize this term, guys? Can you tell me what this term is? It's the variance. Exactly. It's the variance. It's the variance of xi. So what you have is the following. You have the variance of xi plus the square of the mean of xi. This is the mean, remember. Right now, you should go back to the question. Let's go back to the question. You should go back to the question 8. It says that the mean is 0 and the variance is sigma squared, right? All right, so what I'm saying is that this guy here is equal to sigma squared. And this guy, this is the mean, right? This is the mean is equal to 0, right? So what you have is sigma squared plus 0 minus sigma squared outside. All right. All right. Now sigma squared is a constant with respect to I. So what you have is k multiplied by n times sigma squared minus sigma squared. Right. Now this is equal to 0 if k is equal to 1 over n. All right. So that completes the first part of the question. So the first part of the question, the answer for that is as follows. Is 1 over n times this is an unbiased estimator of sigma squared. All right. Are you guys okay with this or not? I just finished doing part 1 of question number 8. You okay with this? Hello guys, talk to me. Yeah, thank you. All right, now to do part 2, to do part 2 of question 8. All right, we have this estimator. Let me write it down one more time. We have this estimator 1 over n times the sum of xi squared, right? Now, in part 2, we are assuming, you should read the question, guys. In part 2, we are assuming that xi are normal with mean 0 and variance sigma squared, right? So I'm going to put that here. So xi, I assume to be normal with mean 0 and variance sigma squared. All right. Okay, the next thing is all right. The next thing you remember. I mean, I did many examples. Like to standardize the normal variable, you subtract the mean and divide by the standard deviation. So that's what I'm going to do here. You see what I'm doing here? I'm dividing this variable by the standard deviation. So what you will get is the standard normal variable, right? So this guy here becomes the standard normal variable, right? Now sigma is a constant, so you can pull it outside. So this is sigma squared by n times the sum of a standard normal variable. All right, now let me check your memory now. You may recall that when we did this some time ago. If you look at the video on the chi-squared, if you look at the video on the chi-squared distribution, which I did some time ago, in that video, I gave a property of this. That is, if you square a standard normal, variable, you get the chi-squared variable with 1 degree of freedom. That's because of, I mean, that's one of the properties I mentioned in the video. I mean, if you forgot, if you forgot that, please have a look at the video one more time. That is, if you square a standard normal variable, what you get is a chi-squared variable with 1 degree of freedom. Now, another property I mentioned in that video is that if you sum independent chi-squared variable, what you get is a chi-squared variable with the degree of freedom being the sum of the degree of freedom of the individual chi-squared variables. So it's sum of 1 for I from 1 to n, which is n. So both these properties, the step from this line to this line and the step from this line to this line both follow because of the properties of a chi-square distribution, which I mentioned earlier in one of the videos, right? So if you have forgotten, please go and have a look at those. Okay. All right. So this completes the solution to question number 8. Are you okay? Is there something you would like to ask me before I go to the next one? Hello, guys. Talk to me. Is this all clear to all of you or not? If it's not, please feel free to say so. I will. Okay, thank you. Thank you, guys. So let me go to the next question, which is question 7. So I'm done with question 8. Question 7 is this. You have a sample of size 10 from a normal distribution with parameter 48 and 36. The first part is to find the probability that the sample variance is between 25 and 60. Right, okay, let me show you how to do this. Right, so this is question 7. You have x1 to xn, sorry, x1 to x10, which are IID, and from a normal variable with parameters 48 and 36. Okay, all right. So let me close this. All right. Now, part 1, part one of the question is to find the probability that the sample variance S squared is between 25 and 60. Now you may recall from a long time ago, I gave you two formulas for the sample variance, where one has the divisor of n and the other one had divisor of n minus 1. And I told you the better one, the one that is better is the one where the divisor is n minus 1. So I'm going to use that one. So its divisor is 10, is the sample size minus 1 times the sum of all right, this is what you get. Yeah, you remember this formula, guys? From I showed you this formula a long time ago, you may recall. Okay. Now 10 minus 1 is 9. So I'm going to multiply across by 9. So you get 9 times 25. Okay. All right. In the next step, I'm going to divide all three numbers by the variance, which is 36. The reason for that, I will explain in a minute why I'm doing this. So I'm dividing everything by 36, which is the population variance. Right. Now, can I ask you something? What do you know about this? Do you know something about this? It's a property that I talked about in the video on chi-square distribution. Okay, let me write it down if you don't remember. If you have a random sample x1 to xn, which are IID from a normal variable with these parameters, right? Then the following is true. All right. Do you remember this property, guys, or no? This is a property I mentioned in the video on chi-squared distribution, right? Okay.
喂，妈妈。
Hello, guys. Mute. All right, let me mute people here. All right, okay. So using this, so what you have here on the left-hand side is the same as this. So because of this property, this guy here must have a chi-square distribution with 10 minus 1 degree of freedom, which is 9. All right. So using this property, the above becomes, now this you can simplify to 25 by 4. And this is chi-squared n minus 1, which is 9. And this you can simplify to 15. All right, guys. All right. So now this you can write as the difference of the following probabilities. Yeah. All right. Now what you have here, guys, is this guy here is the dense sorry. This guy here is the CDF. Is the CDF of a chi-squared variable with 9 degree of freedom at 15. And this guy here is the CDF of a chi-squared variable at 25 by 4. Right? Okay, now I know we did the R session last week. In R, you can compute this guy here using the following command: p-chisq, comma 15, sorry, in brackets 15 with df. Df stands for degree of freedom, equal to 9. And you can compute this using the similar command: p-chisq, open bracket 25 by 4, comma df equal to 9. All right, so this is the answer to part 1 of question 7. Are you guys okay with this? Hello. Talk to me, guys, please. Are you any questions you want to? I mean, please let me know. Are you okay with this part 1 of question 7? Before I go to the next part. Are you sure? Okay, thank you. All right, now part 2 of questions. Part 2 of question 7. So I'm done with part 1. Part 2 is asking you to find the sample size so that this probability is equal to 0.9. All right, so, okay. So this is still question 7, part 2. We want to find the probability that s squared greater than 20 to be equal to 0.9. All right. So that's the same as saying, remember the formula for s squared is 1 over n minus 1 times the sum 1 to n, I mean n greater than 20 is 0.9. Okay. All right, guys. Now I'm going to multiply across by n minus 1, so you get 20 times n minus 1 is 0.9. Okay. All right, next thing is I'm going to divide by the population variance, which is 36, as you remember. So I'm going to divide by 36, which is the population variance. All right, now, because of what I mentioned in the previous page, you may recall this result again, okay? Because of this fact, right? This guy here on the left-hand side must have a chi-squared distribution with the degree of freedom equal to n minus 1. You follow me? And this guy here can be simplified to, if you divide by 4, you get 5 times n minus 1 divided by 9. Okay. All right, now I'm going to write the left-hand side as 1 minus the probability that the chi-squared variable is less than or equal to this, right? Right, now if 1 minus this is equal to 0.9, then this probability must be equal to 0.1, okay? And once again, in R, if you're using R, you can compute this probability using the following command: PCHISQ, open brackets, at this with the degree of freedom equal to n-1. Right, and this is equal to 0.1. Right, now if you solve this equation in R, I mean, I won't be able to solve this now. You have to solve this using R. You will get n is a sample size we are trying to solve for, to be approximately equal to 15. All right, so that's the answer to part two of question 7. You guys okay with this? Any questions? Is that a 9 or a G? Matthew Taylor. It's a 9, so it's a 9, Matthew. There's no G in this question. It's 9. It's 0.9. Yeah, 0.9 all the way. Yeah, 0.9. Yes, you're right. So you should type this command, Vikram, and ask you to solve it. Then it will give you a number that is close to 15, right? So remember, n has to be an integer. So it will give you. So you get the closest integer, which is 15. Yeah. Any other questions, guys? So we are done. Any other questions on question number 7? All right, so let's go back to this problem sheet. So we've done question 7. The next question is question 6. It has 2 parts. I may just have time to do the first part, right? So let me do the first part. So you have a random sample from a Poisson, and the question is to find the mean and the variance of lambda hat, which is x bar. All right, so let me show you how to do. This is question 6. You have a random sample x1 to xn, which are IID from a Poisson distribution with parameter lambda. And you have the estimator for lambda hat, which is x bar, the sample mean. The first part of the question is asking you to find the mean and the variance of this. So the mean is this, right? And this you can write as this, yeah. Taking the expectation inside, you get 1 over n times the sum of the expectation of xi. Now remember, for a Poisson variable, the expectation is, I'm sure you know this, expectation of a Poisson random variable is lambda, right? Yeah. So this is gonna be 1 over n times lambda, which is lambda. Yeah. Now to find the variance, of lambda hat, you say this is variance of x bar, which is the variance of this. Yeah. Now taking the variance inside, n becomes n squared. So n, right, once again, for a Poisson random variable, the variance is, I'm sure you know what it is, right? The variance of a Poisson random variable is also lambda, right? So this is 1 over n squared times n lambda, yeah, which is lambda by n. All right, so the mean of lambda hat is lambda, and the variance of lambda hat is lambda by n. So by the central limit theorem, you can say that lambda hat has an approximate normal distribution with mean equal to lambda and the variance equal to lambda by n. Right. So this is part one of question 6. Part two is easy, really. It's not really difficult. Part 2 you should be able to do by yourself. But anyway, on Thursday this week, I will post the full solutions to all 10 questions. So I will, if you go to the course website on Thursday, you will see the typed solutions, the handwritten solution, and also video solutions. So there are three versions of solutions to all 10 questions in the tutorial sheet number 6. All right, guys. So, and plus on top of that, if you have questions, you can contact me 24/7 by email, Skype, Zoom, or phone. You know my phone number is 0161 273 2941. All right, guys. So have a good afternoon or good morning or good evening, wherever you are. And once again, please, if you haven't done quiz 5, please do so. I mean, there's no excuse for not doing quiz 5 because I have done 20 questions. I have worked out 20 questions on quiz 5. I mean, on questions similar to quiz 5. So you shouldn't have an excuse for not doing quiz 5. So please, once again, please try to submit your answer for quiz 5 before 10 a.m. On Thursday, 18th of March. Right. Thank you. Right, guys. Have a great day wherever you are. I will talk to you soon. Okay. Hello, guys. You okay? Hello, guys. Sorry for taking my time. All right, welcome to the tutorial number 6. The tutorial sheet for this week is, if you haven't seen it already, is this one. This is the sheet. Come on. As you can see, there are 10 questions. I will try to do as many as I can. So I will start with question number 10 and work backwards, because question 10 is the most recent stuff I have done. All right, so I will start with question 10 first. All right. Okay, guys, so question 10. Okay, before that, let me change the camera. Here we are. Excuse me. Hopefully you can see this. So question 10 is this one here, right? So you have a random sample from a binomial with parameters m and p, and you have p hat as this estimator. Okay, and the question is to find the bias and the variance of the estimator. All right. Okay, guys, so let's see how we can do this. So I'm starting with question number 10. You have a random sample, excuse me. You have a random sample from a binomial with these parameters, and you have the estimator p hat, which is x bar plus 1 divided by n plus 2. Right, the first part is to find the bias. So we want to find the bias of p hat. You may recall that the bias is defined as the expectation minus the parameter that you're trying to estimate. Okay, that's the definition of bias. All right, now, so this is the expectation of x bar plus 1 divided by n plus 2 minus p. Now, if you take the expectation inside, you get this, right? By the way, any questions you guys have, please use the chat room, right? Right, please feel free to choose the chat room. The x bar, remember, is the sample mean. Okay, right, now if you take the expectation inside the sum, you get 1 over n times the sum of the expectation of xi. Okay, now do you guys remember the expectation of a binomial variable with parameters m and p is? Do you remember what that is, guys? I'm sure you know, guys, what that is. The expected value of a binomial variable with parameters m and p is m times p. Do you remember that? Yeah, I'm sure you do. Yeah. Okay. Right, now mp is a constant with respect to I. So what you have is n times the constant, which is n times mp. Okay, like this. Right now, if you simplify this, this is what you will get. All right. Okay, so this is the bias of the estimator for P, right? Now, as n goes to infinity, if you take the limit of this as n goes to infinity, the first term goes to 0. So you have 0 minus P, which is minus P. Okay. All right, so since the limit is minus P, what you can say is that the estimator P hat, right, is not asymptotically unbiased. Remember when I talked about point estimation, that an estimator is said to be asymptotically unbiased if the limit of the bias as n approaches infinity is 0. But in this case, it's not 0, it's minus P. And therefore, P hat is not asymptotically unbiased for P. All right. So this is part 1 of question 10. Are you guys okay with this? Or before I do the next part, can you tell me? You talk to me, guys, please. Are you okay with this, guys, or no? Okay, thank you. All right, so let me do. If it's not okay, just please say so. I will go through it again. I mean, I have all the time for you guys. So if it's not okay, please let me know. Okay, now part two of question 10 is to find the variance of P hat, right, which is the variance of x bar plus 1 divided by n plus 2. Okay, yeah, so this will be the variance of x bar divided by n plus 2 plus the constant 1 divided by n plus 2. Now you may know from probability 1 that adding a constant or subtracting a constant does not change the variance. So this is the same as the variance of x bar divided by n plus 2. Okay, you follow me? All right, now this constant, you can pull it outside. So this becomes 1 over n plus 2 squared times the variance of x bar, which is 1 over n times the sum of xi. All right. Okay, now you can pull the n outside, so it becomes 1 over n plus 2 squared, n squared times the sum of the variance of xi. Now, I'm sure you know that the variance of a binomial is, come on guys, you should know this, right? I'm sure you know this, right? The variance of a binomial random variable is mp times 1 minus p. Yeah. Yeah. Now this guy here is a constant with respect to I. All right. So what you have is multiplied by n. Yeah. Now this n cancels with one of these. So what you get is m yeah, and as n approaches infinity, this goes to 0. All right. Okay, so that's the answer to part 2 of question 10. Are you guys okay with this? N plus 2, sir, because the question says n plus 2, sir. If you read the question, sir, it says the p hat is x bar plus 1 divided by n plus 2. Yeah, that's why you have n plus 2 here. Is that the question, Christian? How did you get rid of n plus? All right, how did I get rid of this? This is a constant, right? This is a constant. So if you add the variance of a variable plus a constant, it's the same as the variance of the variable. I thought you know that. Because in other words, adding a constant or subtracting a constant does not change the variance. So these two are the same. Didn't you learn this in probability 1, guys? That if adding or subtracting adding a constant to a variable does not change the variance. All right, so this is equal to this. Yeah, okay. Yeah. Yeah, the variance of a constant is 0. Yeah, you're right. The variance of a constant is 0. Any other questions, guys? Any other questions on number 10? Hello, guys, talk to me. You okay? All right. Yeah, that's right. Yeah, when you pull the constant outside the variance, you need to square it. Yes, you're right. So this n plus 2 is a constant, and when you pull it outside, you have to square it. All right, so we are done with question 10. So we are done with this. So let's move on to question 9, which is this. Here you have a random sample from a uniform, and you have this estimate for theta. And the question is once again to find the bias, and because the first part is to find k such that this estimator is unbiased for theta. All right, so let me show you how to do it. And all right, let me show you what to do it. Excuse me. So this is question number 9. Question 9. You have a random sample x1 to xn, which are IID from a uniform distribution on the interval 0 to theta. All right, and you have the following estimator for theta, which is k times x bar. All right, the first part is to find the bias. So the bias of theta hat, remember, is the expectation minus theta, right, by definition. Right, so this is the expectation of k times x bar minus theta. K is a constant, so you can pull it outside. Right, so this is k times the expectation of 1 over n times the sum of xi minus theta. Now you should take the expectation inside, you get k over n times the sum of the expectation of xi minus theta. All right, now do you remember the formula for the mean of a uniform variable? If you don't remember, let me remind you that if you have a variable x that is uniform on the interval a to b, then the expectation of x is equal to a plus b divided by 2. I'm sure you remember this, right? Don't you? Do you remember this or no? Yes. So using this result, the expectation of xi is gonna be k divided by n times the sum of theta by 2 minus theta, right? Now theta by 2 is a constant with respect to I. So this is k over n times n theta by 2 minus theta, right? The two n's cancel, so you get k theta by 2 minus theta, right? And this is equal to 0 if k is equal to 2, right? So in other words, theta hat equal to 2 times x bar is an unbiased estimator of theta. Remember that an estimator is said to be unbiased if the bias is equal to 0. So in this case, when k is equal to 2, the estimator has bias equal to 0, right? Is this okay, guys? Hello, guys. Talk to me. Are you okay with this part? Any questions on this? No? All right. So now let me show you the second part of question 9. The second part of question 9 is to find the variance. So I'm going to show you how to find the variance of the estimator 2 times x bar, right? Now, if you pull the 2 outside, it becomes a 4, right? Remember, whenever you pull a constant, you need to square it. So it's 4 times the variance of x bar. This is 4 times the variance of this is n, guys, okay, n. Now, if you pull the n outside, guys, it becomes n squared times the sum of the variance of xi. Now, do you guys remember the formula for the variance of a uniform variable? If you don't, I will write it down. If x is a uniform variable on the interval from a to b, then the variance of x is b minus a squared divided by 12. Do you remember this? Yeah. So this is the result, all right, that I'm going to use in the next step. So using this result, the variance of xi becomes theta squared divided by 12, right? Okay, now theta squared divided by 12 is a constant, so this is simply n times the constant, right? And this simplifies to theta squared divided by 3 times n. And as n goes to infinity, this goes to 0. Okay. So this estimator 2 times x bar is a good estimator in the sense that the bias is equal to 0 and the variance approaches 0 as n approaches infinity. So it has both good properties, right? Okay. All right, guys. So this completes question number 9. Can I move on to question 8, please? Before, do you guys have questions on? Are you okay with this or not? Are you sure? Right. Okay. All right. So let me move on to the next question. So I just finished question 9 and question 10. So I'm going to focus on question 8 now. Question 8, you have a random sample from a population with mean 0 and variance sigma squared. And we want to find the constant k such that this is unbiased for sigma squared, right? So let me show you how to do that. Excuse me. So this is question 8. All right, so you have this estimator for sigma squared. Right, now k is a constant and we want to find k such that this estimator is unbiased for sigma squared, right? All right, now, so what you need to do is to find the bias, all right, and set this to 0 and then solve for k, right? Remember, the bias is this, right? And this is the expectation of this, yeah. Taking the expectation inside, it becomes k times the sum of expectation of xi squared minus sigma squared. You with me so far? All right, now the next step, I'm gonna use a trick. It's not a big trick, but I'm sure you've seen. So the trick I'm gonna use is the following. I'm gonna write you see what I'm doing. You see what I've done here, guys? I have subtracted this term and added the same term. So I haven't changed anything, right? Okay, now you should look at it closely. You should look at this closely. Can you see what this is, guys? Can you tell me what this is? This guy here is what is the variance, yeah? So exactly, guys. So what you have here is the variance of the variable xi. Okay, and what you have here is the mean of xi squared. All right, now if you return to the question, let me show you. In the question here, it says that the mean is 0 and the variance is sigma squared, right? So this guy here is equal to sigma squared, and this guy here, which is the mean, is equal to 0. All right, you follow me? All right, so what you have is the following: k times the sum 1 to n of sigma squared plus 0 minus sigma squared outside, right? Now sigma squared is a constant with respect to I, so you have k times n sigma squared minus sigma squared, right? And this is equal to 0 if k is equal to 1 over n. All right? Are you with me, guys? All right. So what I have shown you, what I have shown so far is that the following estimator with k equal to 1 over m is an unbiased estimator of sigma squared. All right. Are you okay with this or no? Hello, guys, talk to me. So this is part 1. This is part 1 of question number 8. Is everything, is this clear to everybody? Yeah, okay, thank you. All right, now part two of question 8 is asking you to do the following, that if you assume that xi is normal with mean 0 and variance sigma squared, then it's asking for the sampling distribution of this. All right, so let me show you how to do it. Let me try to move this page. Okay, so this is so you have this estimator. Right, and we are assuming now that xi is normal with mean 0 and variance sigma squared. Now the first thing I'm going to do is the following. I'm going to standardize this. Now to remember, standardization means you subtract the mean and divide by the standard deviation. So you see what I've done, right? Now what can you say about this, guys? This one will have the standard normal distribution, right? Okay, so you have 1 over m sigma times the standard normal variable power 2. Okay, are you guys with me so far? Let me know. Now sigma, you can pull it outside, so right, so it becomes, because you have a 2 outside, so it becomes sigma squared divided by n right. Okay, guys. All right, now this is where you need to really use what we learned before. If you look at the video on that I did on chi-squared, you may remember something. I mean, this is something that I covered some time ago, the chi-squared distribution. Third step, you mean this step here? All right, Alexandra, yeah. To go from this line to this line, what I have used is the fact that if you divide a normal variable by the standard deviation, what you get is a standard normal variable, right? So here you have a normal variable with 0 mean and variance sigma squared, and dividing that by the standard deviation, which is sigma, and that will give you the standard normal. Is that clear, Alexandra? Or maybe. I mean, remember, to standardize something, you should have, say x, let me write it down here. You should have x, which is normal with mean mu and variance sigma squared, right? Then x minus mu divided by sigma is standard normal, right? Do you know? I'm sure you know this result, right? Okay, so that's what I have used here. Here you have 0 mean and variance sigma squared. So if you divide this by sigma, you should get standard normal. Yeah. So I have used this result here, which I'm sure you know that, guys, right? All right. Now getting back to this. Now, do you remember that if you look? I mean, this is a video we talked about some time ago. One of the results I mentioned in that video is that if you square a standard normal, right, what you get is a chi-squared variable with 1 degree of freedom. This is a property that I mentioned in this video. In this video, so if you have forgotten, please have a look at this video one more time if you forgot this result. Right, and another property that I mentioned in the same video is the following, that, excuse me, let me try to find the ink. Just so this is where I shouldn't write this here. Okay, here we are. All right, now another property that I mentioned in the same video is that issue some independent chi-squared variable. What you get is also a chi-squared variable, right? With the degree of freedom equal to the sum of the degrees of freedom of the variables that you're summing. So here you have 1 repeated n times. So if you sum 1 n times, you will get n. So the answer, so both these properties come from the video that I did earlier. That is the line from the step from this line to this line and the step from this line to this line, both come from properties that I talked about earlier. All right, guys, so this completes question number 8. Yeah, I know this is a little bit tricky maybe for some of you, I don't know. Are you guys okay with this or no? Or you want me to explain better? Hello, talk to me, guys. Are you guys okay with these steps? All right. Okay, thank you. All right, so the next question I'm gonna do, so I'm done with question 8. The next is question 7. The last step. Okay, somebody wants me to explain. All right, the last step is from this to this, right? I have used the fact that one of the properties in this video that issue some independent chi-squared variable. What you get is also a chi-squared variable, right? But with the degree of freedom equal to the sum of 1 for I from 1 to n. Now issue sum 1, right, from 1 to n. What you will get is n, right? So the degree of freedom is the sum of the degrees of freedom, which is 1 here, right, for I from 1 to n, right? Okay, so that's how I use it. That's why I get n here, because n is the sum of 1 for I from 1 to n, right? I hope this is better. I hope this explanation is slightly better than what I gave you before. Okay, if you want better explanation, please contact me later. All right. All right, so let's go to question 7 now. Question 7. So here you have a random sample of size 10 from normal with mean 48 and variance 36. The first part is to find the probability that the sample variance is between 25 and 60. All right. Okay, let me show you how to do it. So this is question 7. You have a sample size of size 10, okay, from a normal variable with parameters 48 and 36. All right, the first part is we want to find the probability that the sample variance is between 25 and 60. Okay. Now remember, I gave you 2 formulas for the sample variance. One is the unbiased version, the other one is the biased version. And you always prefer the unbiased version over the biased version. All right, so this is probability that 25 less than or equal to s squared. So I'm going to use the unbiased version, which has n minus 1 in the bottom. So this is 10 minus 1. 10 is the sample size, minus 1 times times xi minus x bar squared, right, less than or equal to 60. All right, you with me so far? Now 10 minus 1 is 9. I'm going to multiply everything within the brackets by 9 now. So you get probability 9 times 25 times the sum right. Okay, the next thing I'm going to do is I'm going to divide everything within the brackets by 36, which is the population variance. You will see why I'm doing this in a minute. So I'm dividing by 36 throughout. All right. All right. Now, do you remember something special about this, guys? If you don't remember, let me remind you. This is a property I mentioned some time ago in the video on chi-square distribution. If you have a random sample of size n from a normal variable with these parameters, right, then the following is true. That is the sum, 1 over sigma squared times the sum of this has a chi-squared variable, has a chi-squared distribution with n minus 1 degree of freedom. Do you remember this or no? This is a property I mentioned, I talked about some time ago on the video on chi-square distribution. Yeah. All right, now I'm going to use this property here. What you have here is the same as this. Sigma squared is 36, right? So according to this property, this guy here must have a chi-square distribution with n minus n is 10, so it's 10 minus 1 is 9. So using this property, you can write above. This one simplifies to 25 by 4 less than or equal to chi-squared variable with 9 degree of freedom less than or equal to 15. All right, this simplifies to 15. Right? Are you with me, guys? All right. Okay. Now this probability here, you can write it as right. That's the difference of these two, right? And this, right, what you have here is the probability of a chi-squared variable with 9 degree of freedom less than or equal to 15, right? And in R, we talked about it last week. In R, you can compute this using the following command: P chi sq at 15 in bracket 15 with df equal to 9. And this one can be computed in R using P chi sq 25 by 4 with the df equal to 9. All right, so if you have R in front of you, you should be able to compute. So this is the command in R for computing this probability, and this is the command for computing this probability. So the difference of these two will give you the probability that the sample variance is between 25 and 60. All right, guys. Are you okay with this, guys? Or can I, before I do that, are you okay with this part one? Okay, thank you. All right, so now let me show you how to do the second part of the second part of question 7 is over here, is to find sample size such that the probability that S squared is greater than 20 is 0.9. All right, so this is part 2. This is part 2 of question 7. So we want the probability that S squared is greater than 20 to be 0.9. Now this is same as saying that once again I'm using the unbiased version of the sample variance, right, which is the preferred version. Okay. All right, the first thing I'm going to do is I'm going to multiply. Can you show me the last part once again? All right, it's this one here. Vincent, can you see it now? This is the last part. I mean, you can see the video later on, Vincent. I will post the video solution later. I mean, the video in about half an hour time. So you should be able to see it in YouTube or in the other version. Okay. All right, now first thing I'm going to do, guys, is to multiply across by n minus 1. So this is the probability that okay. All right, the next thing I'm going to do is I'm going to divide by sigma squared. Sigma squared, as you may recall, is 36 in this example. So this is 36, 1 over 36 times . All right. Okay, now using the same property that I mentioned in the first part, which is this one. So using this property one more time, you can argue that this guy here, this guy must have a chi-square distribution with n minus 1 degree of freedom. And this simplifies to 5 n minus 1 divided by 9. Okay. All right. You with me so far? All right. Next, I'm going to write this probability as 1 minus the probability that the chi-squared variable with n minus 1 degree of freedom is okay. Okay. So this implies that the probability that a chi-squared variable with n minus 1 less than or equal to this is equal to 0.1. All right. Okay, guys, so far. All right, now this probability in R, if you're using R, you can write it as PCHISQ with 5 n minus 1 divided by 9 with the degree of freedom equal to n minus 1. All right, and this is equal to 0.1. Obviously, you cannot solve this by hand. You need to solve this using R. And if you do that, you will get n, and we are trying to solve for n, all right? N is a sample size. You will get this to be approximately equal to 15. All right? So just put this in R, you will get n to be approximately equal to 15. All right, guys, so this completes question 7. Are you okay with this? Hello, guys, talk to me. Are you have any questions on the stuff I have done? I mean, on part 2 of question 7. Okay. In the exam, you will not need to use R. Why it must be a chi-squared? Because that's the property, sir. It's a property mentioned in the class. So if you look at the video, on chi-squared, you will see that this is a property that I gave you in the video on chi-square distribution, right? Okay, and it can be proved, but I don't expect you to know the proof, right? I've got a question from Mikhail. Well, it's not a matter of putting this in R. You need to write a function, which I will talk about next week. So you need to write a function to solve this, Mikhail. So it's not like typing this in R will not give you an answer. So you need to write a function that solves this equation, Mikhail, right? And then you will get n to be approximately equal to 15, okay? Why can't it be students D? Because I mean, once again, there's a proof that this must follow a chi-squared and no other distribution, right? This must follow, and it cannot follow students T or any other distribution. I mean, this property, as I mentioned, my friend, it can be proved that must follow a chi-squared and no other distribution, right? I mean, in mathematics, everything can be proved, and the same thing is true in statistics, right? Okay. All right, guys. So that's question 7. Right. Next, the next question I'm going to do is question 6. I think I'm running out of time. I will just do the first part if you don't mind. I mean, I know you guys, maybe some of you are hungry for lunch. You show in UK. Me too. I mean, so this is question 6. You have, if you don't mind, I will just do the first part of question 6. All right. So you have a random sample with IID from a Poisson with parameter lambda, and you have lambda hat to be the sample mean, right? Okay. The question is to find the mean and the variance of lambda hat. So the mean is simply this. Okay. Now, if you take the expectation inside, you get now for a Poisson variable, the expectation is, I'm sure you know this, right? The expectation of a Poisson is what? Is lambda, right? Yeah. So this is n times lambda is a constant, so the sum is n times lambda. So this is lambda. So the expectation is equal to lambda, and the variance is just the variance of x bar, which is the variance of, sorry for running out of time. Just give me 1 minute. I will finish. Give me just be patient for 1 minute, guys. Okay. Now, if you take the n outside, it becomes n squared times the sum of the variance of xi. Now, I'm sure you know, guys, that the variance of a Poisson variable is also lambda. I'm sure you remember this, right? Now, the sum of lambda from I from 1 to n is n lambda. So this is lambda by n. So this is the mean of lambda hat, and this is the variance of lambda hat. So by the central limit theorem, by the CLT central limit theorem, you can argue that lambda hat is approximately normal with the mean, which is lambda, and the variance, which is lambda by n. So this is part 1 of question 6. I have run out of time to do the other parts, but the full solutions to all 10 questions will be posted on the course website on Thursday of this week. So you will see the typed solution, the handwritten solution, and the video solutions for all 10 questions posted on Thursday this week, right? All right, guys. Any questions you want to ask me now? I mean, I know I'm sorry for running out of time, but are you okay with everything I have done today, or something is not clear? Please let me know. Hello, guys. Talk to me. Are you okay? That's because of the central limit theorem. So I talked about the central limit theorem a while ago, right? So this result here follows because of the central limit theorem, right? You may recall I mean, you should look back on the video on central limit theorem. You will see why this is true. Okay. All right, guys. So have a good day. Have a good afternoon, good evening, good morning, wherever you are. I will talk to you soon. Any questions you guys have about my course, my teaching, or anything, just feel free to contact me 24/7 by email, Skype, Zoom, or phone. My home phone is 0161-273-2941. All right. And one final announcement is that the quiz number 5 is due on Thursday by 10 o'clock. If you haven't done so, please do so ASAP. Right. All right, guys. Have a great day wherever you are. Right.